Hello, ladies and gentlemen. Today we are going to be looking at new notation. So something new you've never heard of, but you may have seen it on ACT or Aspire tests or MAP tests. These things called logs. So we're going to start this new part of our unit entitled logarithms. It ties closely to what we've been working with in terms of exponents and exponential growth. So we're going to take a look at logs. You're going to need a scientific calculator as well as that little foldable that I gave you in class. So why are we learning this? Let's consider a crime occurred, okay? We're investigating a murder. According to chemistry reports, the victim has traces of aspirin, 300 milligrams in their blood. Aspirin is known to decay at a rate of 20% per hour in the human body. What we do know is that a friend saw the victim take aspirin, two of them, or 500 milligrams, around 4 o'clock. What is the approximate time of the crime? How can we use this information to find out the approximate time when this person became deceased, if you will, and therefore narrow down some alibis or some suspects, if you will? So let's consider how this sort of thing plays into crime forensics. Well, you know what? We do know a decay formula. In fact, the decay formula we've been working on, we can actually apply in this situation. The initial amount we started with was 500 milligrams of aspirin. 1 minus the rate in the human body is 0.20. And it's raised up to the t power, but we don't know how long. That's what we're trying to find. The 300 milligrams is the amount after time. So that's going to go over here. The amount after a certain period of time, t, there were 300 milligrams left over in that person's blood. So now our job would be to try to solve for t. Well, you know what? I could divide by 500 over here, and that would help me isolate the t a little bit. 300 divided by 500 is 0.6, and then I'd have 1 minus 0.20 raised up to the t. Well, wait a minute. 1 minus 0.20, that's the same thing as 0.8, or 0.8, if you will, raised up to the t. And then we have 0.6. So once we get to this point, we would ask ourselves, okay, how else could I get this t alone? I'm almost there. What do I need to do? Well, I need to go ahead and figure out a way to get rid of this 0.0 or 0.8. Do I divide by it? Well, no, because it's not 0.8 times t. It's 0.8 raised up to the t power. Well, then do I take a root? Well, I can't take the t root because I don't even know what t is. And dividing won't work, and adding won't work, and subtracting won't work. The thing is, up to this point, we have not learned a technique to isolate the exponent here, to get him alone. We have not learned about logarithms yet, and that's why we need to. So we have a system of notation that's called a logarithm to help us solve for variables that are in the exponent location. So this is where your notes start in your foldable. What we need to remember is that a logarithm is just a special way to ask a specific question. Logarithm notation is going to look like this. It's going to be log with a little base of b, a sunk down subscript. Then there'll be a normal number here, okay, equal sign, and then there'll be a number over here. The way this is read is I'd say I have a log base b of a is x, means equals. So the way you'll hear me read it today in this video, a log base something of something equals 5 or whatever it might be. When I read this, what question I'm asking, all the logarithm is saying is what exponent is required to go from a base of b to reach a value of a. So the word log is just simply saying what exponent on b gives me a value of a. And that exponent happens to be the answer that I'm looking for to that question. So in exponential form, we're familiar with things looking like this. We have base of something, a little raised up exponent, and it equals some number, like 3 squared equals 9. That's normal to us. The 3 is the base, the 2 is the exponent, the 9 is the value it equals. But when you write things in log form, everything sort of switches around. We end up saying what exponent, which is the same as the word log, on the base of 3 gives us a value of 9. What exponent on the base of 3 gives us a value of 9? Well, that'd be 2. So in log form, things sort of are rearranged. In words, we're going to say we have a log with a base that reaches a value if I am equal to this exponent. Okay? What, what exponent on this base gives me that value? The exponent is the answer. So our notation sort of just switches around. It takes some getting used to, and we're going to practice quite a few on the next 2 pages, okay? So I'm actually going to start on the right-hand side here when we convert between exponent and logarithmic forms. So notice on this side, all of these have exponents in them. So this is exponent form. Notice this whole column has logs in it. So we want to be able to convert from exponent form to logarithmic form. If this is already in exponent form, what would its logarithmic form look like? Well, we would say this is a log with a base of, what's the base in this whole expression here or equation? The base is 1/5. So we say I have a log base 1/5, and that value would be y, and it equals the exponent of x. So what exponent on 1/5 gives me a value of y? It's x. Let's do another one underneath. 9 to the y equals x. We'd say log base 9 of x equals y. So we say log base 9, then we go over here to the x equals y. It's kind of that loop is happening. Log base 9 of x equals y. This one would be log base 6 of x equals y. So all of these you need to convert into log form. I'm going to stop right there and I'm going to check your notes when I see you again to make sure that you have the rest of that filled out. Now let's work down the log column. This is already in log form. So how can we turn it into exponent form? Remember, exponent form starts with a base, exponent equals value. So what's the base on this log? The base is a u. So this is rewritten as u to the v power equals 15/16. Let's do this one. What's the base here? 7/4 raised up to the y power equals x. Oops, 7/4. I better put them in parentheses there. And the last one here that I want to do with you, this one has a base of u. So it's a u to the -16th equals v. Loop around. U to the -16 equals v. We're asking ourselves what exponent on u gives me a value of v? Well, -16 appears to be that answer if I knew what u and v were, right? So again, see if you can come up with the correct notation for those last 6 there in your notes. So I feel like we're going to spend quite a bit of time just practicing the conversions, but we also need to figure out how we can get values from our calculator or even our brain if we know them offhand, okay? So to calculate logarithms, we can do so in our head if we recognize certain special powers, if you will. Like this second one here. Log is asking what exponent on 4 gives me 16. What's the answer for that? Well, that's just 2, right? 4 to the 2 power gives me 16. 4 squared does give me 16. So the log equals 2. Well, what if I can't think of them in my head? What if I can't remember what they are? Even though this one might not be so bad, what exponent on 2 gives me a 4? Well, what exponent on 2 gives me a 4? That'd be a 2, right? 2 squared would be 4. So some of them will be obvious and you might be able to think of. But if you can't, we can turn to our calculator for help. The only problem is calculators need to use a very special way to type them in, essentially. You have to be very careful. So log base of A, big B here, we type it in our calculator this way. This is what I use to type in my calculator. If the problem starts like this is how I'm going to type it in my calculator. So for this first one, if I couldn't think of what power on 4 gives me 64, I can ask my calculator to come up with it. I would type it in as log of 64 divided by log of that little 4. Okay, log of 64, make sure you close the parentheses in case some parentheses pop up on some calculators, divided by log of 4. What's that answer? 3, right? So we come up with a value of 3. So that log equals 3. That value is 3. What about this one? Log base 6 of 216. What about this one? Log base 3 of 100 or 1 243rd. Log base 5 of 125. All of these, if you can't think of what they are, you can turn to your calculator and ask. I'm just going to work down this column here. What about log base 5 of 125? Well, let's type this in our calculator and ask. We type it in as log 125 divided by log of 5. And if I type that in my calculator and hit equals, be sure to close parentheses when you need to, you should come up with an answer of 3. Okay, equals 3. This one down here, log base 2 of 16. What if you have log 16 divided by log of 2? You can type that in your calculator and see what happens, okay? Log 3, base 343 and a 7. I type in log 7 divided by log 343. Yes, sometimes you do get negative values like on this one, okay? So I've set up a few. I've actually solved a few with you. I'm going to leave you some of these fraction ones to try on your own to see if you can figure out how to type them in your calculator. And then I'm going to check those in your notes tomorrow and we'll talk about them, okay? So we've talked about how to convert. We've talked about how to type in our calculator. Sometimes when you just have the log 100, do you see a little base on that? No, right? That little sunken down subscript number is gone. Oh no, what if I don't see a base? If you don't see a base, it means it's a base of 10. That's the same thing that happens on your calculator. When you hit the word log, oftentimes you don't see a spot to put the base. That's because it's assumed to be a base of 10. It's referred to as a common log. So when you see the log of 100, you should know that means it's really log base 10 of 100. And again, we're asking ourselves what exponent on 10 gives me 100? And that answer would be 2. But if you couldn't think of that, you would type in log 100 divided by log 10, and it should also give you a value of 2. Or if your calculator is already set up for log base 10, as they mostly all are, right, you can just type in the log of 100 and see that it gives you a value of 2. Okay, so remember, if it doesn't have a base, it's considered a base of 10. We're going to spend quite a bit of time just typing in our calculator and getting used to the notation in the coming days. Okay, I want to thank you for taking good notes. See you later. Kincaid out.